That's going, doing the thing. Awesome. All right, so we're on to the next talk now. Hi, I'm Julian. And I'm going to be talking about Go concurrency versus Elixir and Erlang concurrency, and kind of how they're different and how they're very, very similar in some ways at the low level anyway. Yeah, I've done this talk before at the Go Meetup last month, so if you've been to that one, I know Braden has, maybe a few others seen it before, but it's kind of the other side of it, doing the same talk for an Elixir crowd, so we'll see how it goes. So about me, my name is Julian. Currently a senior staff engineer at One Digital. We do One Pass, which is like you might have seen the ads on TV with a asthmatic penguin scanner card. And I've been dealing with crippling shared state concurrency since 2000 in Java with threads. It's really bad. Playing around with Erlang since 2007. It's very cool. I love Erlang. Elixir since 2012, so sort of jumped on that pretty early. And I started this meetup back in 2015. I'm still kind of involved as a sort of organizer, but mostly these guys doing things. And I've been doing Go hot takes since last year, which apparently you can learn Go in like an afternoon, so that's actually more like 10 Go years, so I don't know. So what we're talking about today are the design goals of each of the runtimes. We're kind of talking about the low-level stuff, so not really the language or the semantics, but more like how do they actually operate. How they're common, how they're different, how they're actually implemented under the hood, strengths and weaknesses both, and then the main thing is we're wanting to contrast them to learn something about how each of them works. Just show of hands, who's familiar with Go here? Elixir, Erlang? Yep, a few, so sort of about the same. All right, so what we're not talking about is dumping crap on each language and how bad they are in different ways. Because Go is a language that's got diverse error handling. It's deliberately very simple and streamlined standard library. Elixir will make you handsome and tall and awesome, but we're not going to dwell on that. So Go, if you don't know about it, it comes out of Google, designed by Robert Grissner, Rob Pike, and Thompson. And it's really focused around productivity and performance. The use cases are really for building highly scalable concurrent network services, so HTTP servers, that sort of thing. Legend is that Rob Pike got into a 45-minute fist fight with a C compiler, and then he was all like, I'm going to build my own language and make it fast and concurrent. Touching on Erlang /Elixir /Beam. Erlang's the original language. Beam is the virtual machine it runs on, which stands for Bogdan/Bjorn's Erlang abstract machine. And then Elixir is obviously what this meetup is about. It's around since 2002, but they all compile down to Beam as a thing. So for this talk, I'm going to try and just say Beam, and I mean all of those things. I mean Erlang and Elixir and Beam. I'm just going to say Beam. If I mess up and say something else, I mean Beam. That's what we're talking about. So the virtual machine rather than the languages that run on top of it. So Erlang, design comes out of Ericsson in the 80s. I think it was open sourced in the late 90s, early 2000s, by Joe Armstrong, Robert Erding, Mike Williams. And it's got a bunch of very different design goals. It's really focused around fault tolerance and soft real time. And by soft real time, we mean things that are not hard real time, like a hospital or military or avionics or even an inkjet printer. They have to run in hard real time. It has to do the exact thing at the exact millisecond. Soft real time means it's got to run. It's got to keep making forward progress. You can't have anything that will lock it up. So it's always able to keep working and doing stuff and respond as fast as it can. And the use cases are really around highly fault tolerant concurrent telco services. So networking switches, telco switches, that sort of thing. The whole idea of it, it's not allowed to go down. It's got to be hot upgradable. So a lot of the design comes out of that and the fault tolerant side of it. So Erlang, made by one of the guys, Joe Armstrong, creator of Erlang. Different guy to Billy Joe Armstrong, lead singer from Green Day. Different people. If you Google them, you probably end up with Billy Joe, but Joe is the one who made Erlang. Elixir. We kind of know and love Elixir. We're here for the meetup. So this came out of 2002, open source. It's really Erlang, but nicer. It's more Ruby. Not going to talk about it a whole lot because we're talking about the internals, and this is just the thing that runs on top, but it's nice. We all love Erlang. We all love Elixir. So yeah, same use cases as Erlang, probably more targeted towards Go's sweet spot of doing HTTP servers. and web applications, but you can do a lot of other things with it. We dip into the actual design goals of those things. So Beam, talking about fault tolerance, soft real-time. Go, we're talking about productivity, performance. Not to say that you don't get those things from the other ones, but these are kind of what they're focused on when they're building these languages. So Go, they're really focusing on how to make C, but the good bits. It's very simple. It gives you safe concurrency in a way, garbage collected. And performance gives you fair concurrency, which means that things will run without anything being able to dominate the runtime. So you can have a whole bunch of things running and they'll each get a share or different things. Parallel, I'll touch on the difference between concurrency and parallel in a minute. And it's compiled. So all the stuff around concurrency, garbage collection, everything that's compiled into a static binary. So it's got to bring its own, stuff with it. It's like going camping. You've got to pack your own tent and pots and pans and all that stuff and carry it with you. With Beam, really focused on fault tolerance. So web concurrency again, safe concurrency, meaning it's hard to blow your foot up by having shared threads or anything like that. It's parallel, distributed, immutable, isolated. And a lot of these things come around out of fault tolerance. So it wasn't like they kind of said, we're going to make a functional language, we're going to have immutability, we're going to have all these different things. It's more like, no, we're going to have a fault tolerant language first. Then the other things like immutability and functional programming, all that stuff is sort of a second order effect of wanting a thing that's fault tolerant is the primary goal. And in terms of soft real time, also get fair concurrency. It's got to run in parallel. Data is isolated between different processes, and it runs on a virtual machine. So it doesn't have to have all the machinery compiled into it. It just compiles down to opcodes, and then the virtual machine, when it's running, takes care of all the nuts and bolts of how to make all this stuff run in parallel. So when we talk about concurrency versus parallelism, what do we mean by that? So there's a whole talk around this. I think Rob Pike, one of the Go creators, this like concurrency is not parallelism, or parallelism is not concurrency. But it's really talking about how different things that get a little bit conflated. We just want to separate what they mean. So concurrency will really talk about the structure of the program. So you've got a bunch of tasks that can run, and they have a number of steps in each one, and they're sequential steps that run one after another. And you have traditional kind of programming, you might have loops, you might have function calls, all the rest. And they don't interfere with each other, they don't interact. So they can run at the same time, one can run before another one can run after another one. They're not really have any constraints on how they execute in terms of each other, but they will have some way of coordinating the work they do. So there'll be some way it's messages or like a shared kind of state where they can coordinate and rendezvous when things need to come together. With parallelism is the actual nuts and bolts of how you make it run. How do you put multiple concurrent tasks onto different CPU cores or different CPUs or whatever at runtime and make it happen? So the question is how you get from concurrent to parallel. So you've got a lot of concurrent tasks, got a finite amount of hardware. How do you actually make them all run? So one approach is that you could use an operating system per task, which is way too heavyweight. If you've got hundreds of thousands or millions of tasks that need to run, that's not going to cut it because it'll kill pretty much any computer even these days. You might be able to do it, but it's going to be horrible. You could have a new hardware thread per task, which you probably get away with it these days, but it's still horrible. Each thread has got a huge overhead in terms of startup, memory it cuts around, and then actual runtime, context switching, all the rest of it. So that's a non-starter too. Sort of a thread pool to share tasks is another pretty common approach. Works for some things, but we don't want to have to write the code to actually manage that and make it work. So the approach that both these languages takes is to say, well, let's do this in user space tasks. So each thing will say, well, they'll have a thread pool under the hood, but you don't have to worry about it. It takes work, not for us, we're golden. But for the people who make languages, it's a lot more that you have to do in there to make it work. So what you want to have is lots of user space tasks. So when I say task, I mean, like a Go routine or a thread or a process, just stuff that runs and you want to do lots and lots and lots of them at the same time. So we're really talking about, like we call green threads, is another name for them, just a sequential series of stuff to be done. To do a thing, another thing, step through, and then eventually you're done. Then maybe it loops around, maybe it exits. But it's like a fixed set of steps to be done, run sequentially. We want to do a lot of these in parallel. So then we've got to think about how we schedule these things. So each CPU core can only run one thread per core at once. So the idea being that then you can create essentially one thread per core, so one hardware thread that's running on one core. And then we want to spread those tasks out so that they're equally used among all those threads. We get sort of efficient use of all the cores running on all the CPUs. And then you have a way of scheduling those tasks to run, and then the threads can kind of work through them. So that's kind of a simple approach there. You can say, hey, we just have like, a bunch of threads. We're going to set up a run queue for each one, and then you load the tasks into each run queue, spread them out so they're all fairly done. And that's great. Like, if you just want to have like a batch job where you're spitting stuff out and say, just run till completion, then do the next thing, and then the next thing, that's great. It'll work fine. Thing is, what if you don't want to do that? If you want to actually have this thing where you don't just want to run to completion, but you actually want to sort of multiplex them. So run this a little bit, run a little bit, run a little bit. They're sort of interleaved so that each one can make progress. Maybe each one is sending bytes over the network, so you don't want to wait for one to finish before you start the next one running all the way through. You can't do real time that way. You need some way of actually spreading them out and actually having them able to respond inside there. So one of the first times when this came up, because computers way back in the day, they would work that way. You'd have like, here's a big job, run it to completion, and the next thing runs, and so on. If you go into the moon, you actually do need to be able to do things vaguely in real time. So Apollo 11, they're putting down the landing, and there's Neil Armstrong and Buzz Aldrin sitting in the capsule, and then they're putting down like 36,000 feet, and they get a 1202 alarm, and everyone's like, okay, what's that? That sounds bad. No, okay, no, we're okay, we'll go, keep going. 1 minute later, that same alarm came up again. That sort of came up a few times, got down to 2,500 feet, so they're like a couple of minutes from landing. And this like 1202 and 1201 alarm is going off over and over and over. And mission control was basically like, no, we're good, keep going, proceed. Everyone's kind of like panicking, what is this thing? It's bad, but it's okay, we can keep going. And they got down, and the rest is history. They put a flag and did some other stuff and came back. Didn't play golf. Some other guys did that a couple of flights later. So the cool thing with that, like, they had this thing, like the Apollo guidance computer, which is a remarkable bit of hardware. Heaps and heaps of documentaries about this online. So you can go and watch them because it's really fascinating to learn how this thing works. But what those alarms were basically saying that this computer was overloaded. It had too much work that was being pumped into it. What it turned out is the rendezvous radar, which is pointing up into space when they go back. They're rendezvousing back with the command module again. That would tell them how far away they were. Don't need that when you're going down onto the ground, because you want the down radar, not the up radar. But there was a fault that was pumping heaps of data into the CPU, telling it to do a lot of work. And the computer was getting overloaded, but this thing was designed in a way where it said, yeah, I'm overloaded. I'm just going to kill some work. Here's all the low priority tasks, rendezvous radar. No, don't care. You want to like actually input flight controls and fly the thing? Yeah, that's the priority. I'm going to make sure that happens. So it worked really well. And so sort of with that soft real time, it actually said, okay, every 10th of a second, you made sure you could, work the flight controls, and that worked. So what it did is it could shut down and restart super quick. And so that was essentially how it did concurrency. Like, it queued up a whole bunch of work. Each one's going to take a very short amount of time, like a 10th of a second. If it saw more work in there for the next second than what it knew it could get through, it would just, sort of truncate the work queue and just shelve some of the low priority work. So this is kind of what we're looking for. We don't want to like kill stuff off. We want to have a way of saying, if something's going to run too long, how do we actually mitigate that and make sure the rest of the system can still make forward progress? So we need a way to share the resources. We've got hardware resources between a whole bunch of tasks. We might have arbitrary many tasks, finite hardware. There's a couple of main approaches to this, and there's cooperative multitasking and preemptive multitasking. So cooperative multitasking is simpler in a lot of ways. This is what you see coming up a lot, and it works pretty well up to a point. The idea is you run tasks until you hit a natural breakpoint. Like, that might be sending some bytes over the wire, it might be reading a file, basically generally some kind of I/O. Or it could be like a manual yield. So if you've got a long running computation, say, I'm going to stop now, let someone else have a go. But you have to manually put that in the code. Simple to build. If you've got the runtime like this, pretty easy to put it in place. Less overhead. One of the good things about it is that tasks know when to context switch. So you don't have to have the overhead of like, preserving state, getting something else to run. You say, I'm done with this bit, let someone else go, carry on. And so if you see anything with like an async await keyword, so JavaScript, Python, Rust, they'll kind of work like this under the hood. So Node.js is kind of a classic example of this. So it'll run a bunch of stuff till it gets to a kind of natural breakpoint, usually some IO, then it'll kind of yield and let something else run. And then it'll run like one loop per thread, and then you can start multiple of them in process if you want to put some kind of hardware concurrency there. But cooperative multitasking is kind of like cooperative multitasking if you've ever lived in a student flat. So if you've lived there and you have a kitchen and that's shared and that's fine, everyone just goes in, cooks their meal, cleans up, someone else has a turn. And you get one dude who's going to let the big bacon and egg fry up on Saturday morning and then just leaves dishes there. So that's kind of the downside of cooperative multitasking. There's nothing stopping one thing from saying, I'm just going to keep going. And that's why you don't want to use Node.js to land on the moon. So the other approach, so neither Go or Beam does cooperative multitasking. They do the other one, which is preemptive multitasking. So this is where the runtime kind of does the hard work of figuring out when to interrupt things. Gives you more reliable behavior. There is more overhead to it. So the runtime doesn't know when a good place to stop each of these tasks running is. So it's got to do work. It's got to reach in and kind of grab all the CPU registers, store them in state somewhere, let something else run, and then back up again when it's going to come back in. So yeah, it's more complicated to build. But again, it's for the language authors. For us, we're golden. We're great. We can just use this stuff. So this is what we were looking at before. So this is kind of the approach that works pretty well. So you'd have like a CPU, potentially you've got multiple cores, potentially you've got multiple CPUs. There'll be a thread running on each core. And then there'll be some code that runs and says, okay, I'm going to grab a task off a request queue, run that thing, run the next thing, run the next thing. Question is, are we talking about Go or Beam here? Yes, they are basically the same. Like when you dig down into what they do under the hood, they're basically doing the same thing. They're both implemented the same way. And this is kind of if you're going to do preemptive multitasking, this is what you do. Dig in a bit deeper now. So Go scheduling gets a little more complex if we dig into the details. So it'll have the concept of threads, which is like the thread that runs the actual code. So there'll be a hardware thread. I'll call them an M. So if you look through the Go source code, we'll have M all through there, which sort of means machine, or it's like a representation, the idea of concept of a machine that can do work, like a CPU. Processes, P, are the thing that actually does the work. That's the code that runs. And then Go routines are what Go calls processes. So, that's the unit of work. That's like, you're going to spawn a function, going to have it run in the background, that's Go routine. So they'll start essentially like a thread per CPU core. Each thread will have a processor, which is really data structure and memory. And then it'll have like a Go routine that's currently running. It'll run for a bit, and then it'll have a run queue of other work to do that runs through there. It also starts another thread, so it's not strictly one-to-one. Like you have more threads, which you're going to have in any operating system. You can have more threads than that anyway, because you'll have other processes running in the background. But in terms of what's actually running, mostly one-to-one, but there'll be the sysmon thread that does some background work as well. And the sysmon thread is the thing that is kind of the key to making the preemptive multitasking working in Go. So this is a very, very simplified sort of model of what that sysmon process does. So essentially it runs an infinite loop. It's going to sleep for 20 microseconds. Then it's going to have a reference to all the processes. It's going to loop over those. And it'll have some check to see, has this processor been running for too long? So by default, it's 10 milliseconds, I believe. If that process has been running for more than 10 milliseconds, then it's going to tell it, okay, we're going to preempt you now. We're going to stop you, let someone else have a go. The way it does that is it gets the current Go routine that's running, so that's the p.m.current g. it sets a flag on that Go routine. So it's just a data structure memory. It says preempt is equal to true. That will then cause it to go off and say, I'm going to go and preempt next time it runs through. And it's also got a special way of doing it. So when it's maintaining a stack in there, which we'll talk about in a little bit, but the stack is going to have a bunch of extra flags in there. One of them is around has a stack overflowed. And it puts like a special stack preempt value into that stack overflow check. So the next time it tries to call a function, it's going to say, has the stack overflowed? Oh, I've got the special value in here. I'm going to like bow out and let someone else have a turn. So when you call functions, you might write a function in Go that looks something like that. It's up to my function 1, and it's going to call another function. What it's actually going to do under the hood, this is not in Go code, this will be compiled down to assembly. It's going to say, is the stack guard equal to the stack preempt constant? If it is, then we're going to preempt this, the currently running processor. This Go routine is going to kind of step back, and then something else is going to step in and let it run, and it'll come back in at that point again. And then it would be at the point where it hasn't run my function 2, but it's sort of, it can run that when it comes back. So the thing with Go preempting is that the initial version of it is it's still technically cooperative. So it only preempts at function calls. And this was sort of a problem for a while. Like if you had my function 1 and then you have an infinite loop in there. So in Go, that's just going to say, run this forever, not doing any work, just loop, 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 loop. When it's done, call my function 2, it's never going to get to function 2. But because it's never calling a function, it never got to that special bit of code, just check the stack flags to say, can we preempt now, can we not? And it would go into an infinite loop and it could hang the runtime, which was bad. This is not the case anymore, which is good. So Go from 1.14, which came out a few years ago. This at the top is all the same down to the preempt processor line. That's exactly what we saw before. So that puts an extra thing in there saying we're going to preempt the processor, and it does an extra step, which will do an operating system signal sends to the thread. And so then there'll be some, like a sort of registers a callback to say, okay, when we receive the signal, go and do some special work. And that special work is to say, okay, pause this processor, even if it's in the middle of one of those busy for loops, and preempt it anyway. So it's good. It actually gives you proper preempt multitasking in Go now. All right, so moving back to Beam. Again, it's very, very similar. So the same basic idea, you have a CPU, you've got a number of cores in there. It'll start a scheduler thread for each core. Each scheduler thread will have a scheduler data structure. There'll be a number of processes, and there'll be a ready queue and a waiting queue. Waiting queue is stuff that's not ready to do anything, like it might be waiting on I/O, it might be waiting on a message receive, it might have to send a message receive, it might not be its turn to go yet. But essentially it's going to round through those things. So it'll go through the ready queue, give each one a chance to run, then go to the waiting queue and sort of poll that every now and then when data comes in to service one of those. So thinking what scheduling looks like in the Beam, and this is implemented in C code. I've done Go pseudocode here because I'm not doing C pseudocode because that would just be horrible. But the idea is it's kind of similar. So when a scheduler runs, it's going to say, okay, here's our current scheduler. Let's grab the current process that's running in that scheduler, so the current bit. And because it's a virtual machine, we've got an emulator that's going to say, okay, we're going to grab the next operation that this process is going to want to run, and we're going to get the emulator or the, the virtual machine thing that will just run bytecode, do that thing. And then it'll update the state, it'll kind of move along, update memory, do whatever else it needs to do, I/O, whatever. And then the way that it works is not around time. It has the idea of reductions, which is like really, it's a function call. So it'll count +1 reduction every time you call a function, or every time you do like a virtual machine operation. And then it's got a magic number, 4,000. As soon as you get to 4,000 reductions, you say, all right, you're done. You take a break now, let someone else have a go. And it goes from goes off the ready queue, or goes back on the ready queue actually, and then it'll just pop another one off the ready queue, and then that's the one that gets to run the next time around. And then it'll kind of just keep going round and round. So it's a bit of a different approach. So with Go, it just says 10 milliseconds you get to run for 10 milliseconds and someone else gets to go. Beam says you get 4,000 function calls. Which one's better? They're kind of different. Like with Go, if you've got one thing that's really heavy and sort of monopolizing CPU, doing a whole bunch of work, that can sort of grab way more than what it needs to. The other thing's still got a chance to run, but it's like, is that better? Don't know. With Erlang or with Beam, it's going to say, all right, it's got a really heavy sort of process doing a lot of operations. It'll chew through its 4,000 really quick, and then something else gets run. So in a way, really heavy code gets penalized, and then the code that can run very quickly and get out of the way gets a chance to run because it's not really based on time, it's based on the amount of work that it does. So sort of swings and roundabouts as to which one works better. I think this one gives you less chance of sort of locking up because those heavy things will not monopolize the processor as much. So that's how they schedule. Then you've got to figure out how to coordinate them together. So traditionally you'd use like mutable memory with lots of mutexes. It's really hard and that you'll kill yourself doing this, and I have done a lot of time. This is a great book, so a little book of semaphores. It's free online. I think you can Google this and find it. The thing I really like about this, it's got a whole bunch of little exercises we can go through, and it's got really low level kind of mutexes and locks and things. You've got to say, okay, how do we solve this concurrency problem given these tools? And then you kind of do that as an exercise, and then it like walk through the answer. It's like, right, here's all the way you probably screwed it up, and there'll be like 20 ways where you've made a mistake, and things where you don't want to do it, and things where there's race conditions and deadlocks and stuff like that. So if you want to know about how hard shared stack concurrency is and how many mistakes you can make, that's a good resource for it. So both the runtimes give you a sort of safer, higher level way of working with them. So in Go, you've got channels, and Beam, you've got process mailboxes where you can send messages to. So Go channels are based on CSP, or communicating sequential processes. Coroutines are anonymous, so you can't directly reference them. Instead, you have a channel, so you have to like create a Go routine and give it a reference to a channel somehow. Channel is synchronous, so if you put something in, it's got to receive it at the other end, so they'll block unless you've got both the sender and the receiver ready to go. You can have them buffered, so you have a finite size in them, but as soon as it fills up, then you're going to essentially block until one side is consumed out and the other one, or the other one is read if it's written data to it if it's empty. So if you want to have some Go code, it's very, very dumb thing you would not ever do in practice, but say you want to have something that would multiply numbers together, this is sort of what it would look like. So we're going to make a channel, we're going to get another channel to get the result, then we're going to use the Go keyword to call this thing asynchronously. We're going to feed in 6, we're going to feed in 7, then we're going to get the answer out. In the concurrent code, it's going to read each of the numbers out and it's going to multiply them and send them on the out channel again. Pretty trivial, but we'll just sort of use this as an example and we'll come back to that. So in Beam, it's a different setup. We've got PIDs or process IDs, mailboxes, and messages. So there's a reference, they're not anonymous, so you can actually, when you spawn it, you say, here's the thing, it's a value, you can pass it around and do stuff with it. And then you can send messages to it. They go into a mailbox and that's fully async, so that it's not going to block. So you can send messages as much as you want to a channel, and that's fully async. It's never going to block the sender at all. And again, it sort of comes back to the fault tolerance. Like you should be able to make forward progress all the time without being blocked by anything else, unless you want to be blocked by having some kind of protocol for getting data back and forth. But yeah, they don't block. So the similar code in Beam would look sort of like this. This is Elixir. So we're going to spawn a worker, we're going to send the worker a reference to a tuple. It's going to give it, so we'll want to do some work, and we're going to give it self so it knows where to send the result back to. We're going to give it 6 and 7. Then we receive the result back, and we just output it. And in the actual concurrent work at the bottom to do mult, we have a receive block that will pull that off the channel, off its not channel, its mailbox. It'll read from its local mailbox, and then grab the X and Y values, and then send it back to where it came from, whatever the result was. In Beam, you don't really use them very often though. Like if you're directly coding with doing spawning and all that sort of stuff, you're probably doing it wrong because there's a bunch of tools built in that'll do this for you in a much nicer way. So actor pattern is very common. Gen server is basically that. If you've used that before, you can create thousands of them. So the goal there is really around fault tolerance and resiliency, and performance is just a nice side effect of that. So one of the things with Go is that you can do things concurrently in Go, but it tends to make them less resilient rather than more. It's easy to kind of like get into deadlocks or get into the case where things don't come back out again. So here's an example where down the bottom we're saying, if we randomly, we're just going to randomly panic sometimes. What'll happen in this case here is that it'll just hang, like it won't get the result back, and it's just sort of waiting there. Don't know what's going to happen. It's kind of hard to figure it out. Or does it? No, I think that'll actually crash the runtime. So it's sort of not contained the way you'd like it to be. If you wanted to actually make that be handled a bit nicer, you have to do a bunch more plumbing. So you have to create a separate channel for getting errors back, or you have like a same channel and you've got to do some weird stuff because the channels are typed and you can't have like a result and the error coming back through the same channel unless you do like a weird interface thing. And then you select the error coming out of there. And that'll work, but it's sort of a lot of work to actually get it running. So Beam, it's got like a different approach to that. So you might have heard of let it crash before. The idea being that processes can be linked. So if one process dies, the linked processes die too, but the whole runtime as a whole does not die. So the supervision tree is built to take advantage of that idea. So you might think, okay, well, if linked processes die and it kills the one that it's linked to, how's that good? It's like, well, sometimes you want them all to go away as a unit so you can actually restart it as a unit. And if you don't want that, you can monitor it and then kind of control how you're going to make that run. So with Beam, if you're doing that similar kind of thing with concurrent logic, it's what we had before. Here's some code that's going to spawn that thing with a spawn link. We're going to send the work to it. Same deal again. If we randomly get an error, we're just going to raise, and then that'll blow up. That'll cause the thing that spawned it to blow up, but you can contain that. You can kind of have a supervisor and then pick that up. So yeah, supervisors are a big selling point in Beam. So you have a tree of things. Each one monitors and restarts children, and then they can monitor and restart their children. And then they'll restart within a period. And then if you have too many restarted, then the supervisor will restart and back up to the, following up the tree. The idea being you can shut down a whole part of the tree, restart it all again, and it should get you back to a known good state. And the main thing is that no part of the system can affect other parts unless you design it in. Like you can't have it like, you get some kind of weird panic in your web worker. It shouldn't take down like your, like the database pool. So it's essentially turning it off and turning it on again, which is most of how Erlang works, or Beam works. So yeah, this is a bit of code to squeeze on one slide, but this would sort of be what it looks like if you actually wanted to run this in a way that handles it properly. So this is using a dynamic supervisor doing the same thing as what we did before. The work down the bottom with the do molt function that's actually doing the work is basically the same as before. Like there's no change to that. We don't have to do any special plumbing to handle errors. We're just going to say, sometimes it errors out and sometimes it works. But we have a thing that we're initiating it with a function there that will spawn the worker to do the work. So the idea being that if it dies and it restarts, we give it the same parameters to get it back to the same state again. So it can carry on from where it got to originally and then keep going from there. And so one of the ways we build this in is thinking about where memory lives and how it's actually used in memory. So it's going to do a quick recap of CS 101. Two main types of memory you've got to deal with in systems. It's going to be stack memory and heap memory. So recap of heap memory. I've got stack there, which is dumb at the top. Generally said heap for that top word. The idea being that for a stack, there'll be one for each concurrent task. This is the same in Go and same in Beam. And when you have a stack, that'll be the list of all the functions that we call. So it's the hierarchy of this function is called this function, it's called this function. Local variables will live there. It'll have like sort of return addresses for where to go to when a particular function finishes. And the nice thing about the stack is that when a function finishes, you can just roll it back and say, okay, this stack frame is done. Stack pointer goes back to here. And that memory, you don't have to free it, you don't have to do anything with it. It just sort of sits there and you override it when you need to use that space in the future. The other one is the heap, which is really just a big, when you think about memory in a computer, you're mainly thinking about the heap. It's just a big global data, sort of addressable space. And so anything that lasts longer than a function call, anything you need to share around, it's going to live in the heap. The thing with the heap, it's got to be garbage collected or have some kind of manual memory management. But in Go and Beam, they're both going to be garbage collected. So not actually a heap data structure, but it's just a big heap of data. It's really just a big array. That's the best way to think of it. And this is kind of one of the big differences between Go and Beam. So Go's got a single global heap, like you get in almost all programming languages. So each Go routine will have its own stack. So they're isolated, but the heap itself is not. So you can share data between different processes or different Go routines. And then you sort of use the built-in primitives to work with that. You can actually access it directly, and you do have mutexes and locks and all that sort of thing, and you have to do that if you do want to do it manually, which you'll kind of do if you want to get performance. Whereas Beam, on the other hand, has got a different approach where each process has got its own stack and heap, which is kind of unique. You don't see that very often. So the heap for every single process is totally isolated from every other heap, so that you can't actually dig in and get a reference to any data in a heap that's owned by a different process. You can only access your own heap as a process when it's running. So yeah, the Go heap is global. Got some good and bad sides. You can share references, so it's nice and fast. You can share references, which is bad because you get concurrency bugs. Lots of data all in one place. And the garbage collection actually gets harder when you have one single big thing. It can get a lot of junk and it's harder to go through it. Whereas Beam, on the other hand, it's got a heap per process. References can't be shared, so data has to be copied. So that's where the message passing that comes in, and it's really important, because if you want data to be from one heap to be in another heap, you have to copy it and send it via a message, goes into the mailbox, you receive it and pull it out and work with it that way. So that's slow, so that's bad. But it also means you can't shoot yourself in the foot by having multiple things updating the same data at the same time. It also means there's much less data in each heap. So each heap tends to be much, much smaller. And that means the garbage collection gets a lot simpler and it can be a lot faster. So going back to garbage collection really quickly, it's kind of got a couple of phases in there. So there's mark and sweep with a lot of traditional garbage collectors. So mark phase is going to go through all the global data and local variable data that's going to be sort of accessible in the stack. And it's going to mark it as active. Then it'll recursively sort of fan out and find all the references that it can, mark all those references as active too. That phase can run in parallel. Then it's going to go through the sweep phase where it's going to say everything that didn't get marked as active, it's going to sweep it and basically say this is all freed. You can use that memory again. The sweep phase, it does have to stop the world, but it's relatively quick because it's done most of the work already. So in Go, that's pretty much exactly what it does. It's global. There is a separate thread with this run, so it doesn't run within each of these Go routines. It's complicated because it's got to deal with all those data kind of conditions of what's allowed to access what, and thinking about when Go routines can be paused, because you've got to think of, okay, if it's running, can it be preempted at this point? Can you actually access garbage at that point and sort of go through and mutate and mark things as active? I think by default it'll run every 2 minutes, or there's some kind of tunable ratio of whatever the total versus free memory is hit, and then that'll kick it off. So Beam is very, very similar as well. Big difference is that it doesn't run concurrently, so it's local to each process, and each process does its own blocking GC. So you might think that blocking GC is kind of less than ideal, but because there's so much concurrency built in anyway, it means that heap doesn't actually have to do much work because it's just a small amount of data there. All the other processes have still got a chance to run at the same time. That local process just needs to look through a small amount of data. Pretty simple because it's only local data. It doesn't need to lock or preempt anything. And it runs whenever the process heap memory gets to some small size. So you'll typically see in Beam, rather than doing this big kind of garbage collection every now and then, doing lots of little ones all the time. ensures the system's never blocked due to garbage collection being a thing. And also when we talked about reductions before, like you get the 4,000 reductions, means that this can count as part of those reductions. If you've got something that's producing a lot of garbage, that gets penalized and it gets less of a chance to run and impact the rest of the system. For good or worse, like if you've got some bad code, it's good. If you've kind of got code where you want it to do that, that's something you've got to tune. The cool thing with Beam garbage collection, it gets a bunch of superpowers based on that. So because Beam is immutable, means that the garbage collection gets even simpler, because with immutable data, you can't have cycles. So that's a whole bunch of stuff where you don't have to worrying about with the garbage collection algorithm, because, you know, immutable data, old data cannot point at new data by definition. It's just, you know, immutable data doesn't work that way. And also because you've got immutable data, old data can't point at new data, generational garbage collection gets a lot easier as well. So it kind of works out that if you get a lot of new garbage being created, which you will get just due to the nature of having to do lots of, you know, list processing and just the kind of work you do in functional languages, you get a lot of new garbage that can be very quickly dealt with, very little old garbage, and the old garbage is kind of, because it's immutable, it can never be updated to point at things that have been created later. It'll just sort of sit there and you don't have to deal with it as much. So that's kind of nice. Yeah, so in summary, Go supports a lot of processes, reactive, fast, great for online software time systems. Beam, basically the same thing. They're both really good. So yeah, that's all. Thank you. Any questions?
Hi, Julian. I mean, you said they're basically the same thing. I mean, Erlang always outperformed Go because of the garbage collection, but then Go fixed it about 5 years ago. I don't know exactly what they did. I was told it was a very, very smart Russian guy. But what did they do? Because you've described it as being the same way it always was, but they've really changed it and made it fast. So,
I think it's concurrent. It didn't used to be concurrent. Like it used to be stop the world. So it used to be like they'd have the mark and sweep phase in it. But from what I understand, it used to be they would do the whole thing, like everything would just stop and let garbage collection run. Whereas then it's like, okay, you can actually do the mark phase in parallel, and it's just a sweep phase that's stop the world, but that's very, very quick. Yeah. And I think it's not even stop the world. It has to stop every process at some point. Yeah. But it doesn't have to stop them all at once.
Yeah, because it's really quick now.
And it might have been the things. There's also the thing with the busy loop. If you have a for loop that's waiting there, it wouldn't yield inside like a for loop if it's just doing something computational in there. Could be around that as well, because at the same sort of around 5 years ago is when they brought in that optimization to say if you've got like a busy for loop and you're not calling any functions, it'll still preempt it there, because it needed to wait for that to pause for the garbage collection to be able to run, and that would lock everything running.
Yeah, it's impressive that they're still doing it on one huge area.
Yeah. I mean, Go will generally outperform Erlang for a lot of stuff. Definitely in a straight line. When you get under heavy load is where it gets really interesting. Like Erlang will do really well. It'll be very stable and consistent throughput, which I think is really nice about it. Because operationally, to say, you know, it's very predictable as to how this thing's going to run. With Go, you still kind of get spikes. It'll run fast, and occasionally we get a big slowdown, and then it's fast. And yeah.
Thanks.
Anything else? Cool. All right. Well, thank you.
Thank you.